Hello students of statics, this is Dr. Dan Baker, and in today's lecture we're going to transition into a whole new chapter in statics, and we're going to start looking at trusses. Now trusses, you likely have seen trusses if you've ever been up in the attic of your house, or if you've been in other buildings that have more kind of an open architecture. That a truss is essentially a series of slender members. Okay, so here would be an example of a truss. Now I'm going to put a bunch of dots where all these members come together. We're going to call these joints. And so let's say that we had something like this, the dot where all of these members come together. Okay, so this is what a truss would look like. So if we go ahead and define a truss in terms of some kind of more statics, some technical terms, we can say that simple trusses, and we'll get into what is a simple truss versus a non-simple truss. So simple trusses are a structural element made of two force bodies. Now we're going to use the term bodies and members kind of interchangeably here. So a structural element made of two force bodies pinned together into a series of triangles. And so it turns out that this idea of triangles ties right into this word simple. And I'll actually give you an equation later in this lecture to compute how you can validate if a truss is simple or not. Another way you can think about a simple truss is that if a single member breaks, then the truss is actually going to collapse. Okay, so in being simple, there's another term that they sometimes use when they talk about bridges, and they talk about being fracture critical. And I'll revisit that term as well and give some examples. But let's go ahead and start out with a few more definitions. So we talked about that all of these yellow parts here that I've highlighted now, these are the members, right? And all of these are going to be two force members. And you'll remember that two force members can only be in tension or compression. That is the only two options for a two force member. And then tying together these two force members are a series of pin joints. And pin joints fundamentally are going to act exactly like the concurrent force particles that you looked at back in chapter 3. Okay, so just like chapter 3 particle equilibrium. So it turns out that a lot of the skills that you learned back in chapter 3, we now can apply in chapter 6 structures. Now, in order to support these trusses, okay, so they're a structural element, they're basically a series of these two force members and joints, but in the end, they're going to act like a rigid body. Okay, so we know that rigid bodies can have up to 3 external reactions that we could solve for. Okay, of course, if we have a pair of reactions like over here on the left, this would be analogous to a pin, and then over here on the right, this would be analogous to a roller. Okay, so a pin and a roller. Noting that if you want to, you can actually, we think about isolating, draw a little isolation line here, and a note over here to the side that says we can treat a truss like a single rigid body. So one of the things that we're going to learn as we get into multi-body systems, especially multi-body systems that are in equilibrium, is it doesn't matter at what scale you look at a system. It turns out that every single member is in equilibrium. Okay, so that would be an equilibrium. Every single pin joint would be an equilibrium, and every single entire truss would be an equilibrium. Okay, so equilibrium basically moves across all spatial scales. So let me emphasize that a little bit more in another drawing. Let's draw the simplest truss possible. We said that trusses are triangles. Let's make a truss of one triangle. Okay, 3 members, and it's going to carry one single force. Say a force here up on top. We'll draw a problem sketch here. So here is one of our supports. Here is another support, so a pin and a roller. And so we know that if this truss is in equilibrium, we also then can draw a free body diagram. That word equilibrium should key in your brain this idea of free body diagrams for every single equilibrium problem. So we add in our unknown supports, roller here with a vertical support normal to the surface, and our applied force F. To complete our free body diagram, let's add an axis system. Let's call that X, and this is Y. Okay, so once again, we can take our entire truss, create a single free body diagram, and with this, we could go ahead and write equations of equilibrium, right? We could sum forces in the x direction equals 0, we could sum forces in the y direction equals 0, we could sum moment about a point equal to 0, right? Because this acts, like I said, this is a rigid body fundamentally, and so we get 3 equations per 2-dimensional rigid body free body diagram. So as you can probably see that I'm talking more about multiple bodies, multiple free body diagrams, so we're going to gain more and more equations, okay, as we move forward. Now, another way that you could take a look at this same truss, I'm going to scroll up here for this, is I'm going to explode this truss into joints and members. Okay, so taking the same truss, let's go ahead and give it some label points here. Let's call this A, this here B, this here C. Now, before I explode it, let's talk quickly here. Let me label these ones also A, B, and C. Let's talk quickly about tension and compression. Okay, so we've talked about 2 force members. The 2 force members can only be in tension or compression. Often for tension, we use T with some parentheses around it, and compression, we use C with some parentheses around it. You can think of those labels kind of like a positive and negative sign, right? And it turns out that there are going to be some topics later in statics where we're going to assume that positive is tension, and we're going to assume that compression is negative. And so we'll even find out here with trusses. Often with trusses, I find it easiest to assume everything's in tension, and then I have my math check it out and see if anything happens to be in compression. So if we take a look at this super simple truss, one single triangle, if I have a force pushing here from the top, it's going to be pushing compression through both of these legs. And then in order that A and B don't separate, we're going to have tension in this bottom member. Okay, so I'm forecasting here compression on either one of these sides and tension here in the bottom. And I'm going to draw my free body diagrams using that assumption. And actually in this case, you could predictably look at it, and I can tell you for a fact that AB will be in tension, AC will be in compression, BC will be in compression as well, right? Just how those forces work through that system. All right, let's blow this thing up. So make this like, at least a quarter or a half the width of your page, kind of a quarter of a page overall. Draw one joint down here. This is going to be joint A. One joint way over here. This is going to be joint B. And another joint up here. This is going to be joint C. Let's go ahead and add our applied forces. So here's my applied force F. Add our reaction forces. I'll label them this time. Call this one AY, this one here AX, and then a roller force giving us a vertical normal force of BY. At this point, I'm assuming the direction of these reaction forces, same kind of thing. I'll check those with my math. All right, so I'm going to draw the members. I'm not going to draw the members full length because I want to leave some room for some forces coming off the joints and coming off of the members. Okay, once again, I've exploded this. 3 members, 3 joints. All right, so we talked about that these side pieces here were going to be in compression. Compression always pushes. Okay, so we could draw 2 forces on here. I'm just going to call these AC and AC. Pushing there on that member. It's a 2-force member in compression. I also have compression forces pushing on the joints. We'll talk more about this. This is actually Newton's third law where we have equal and opposite forces. And so this is going to be also AC in compression pushing on joint A, right? So just a label here. This one was in compression. Let's do the same thing over here for BC, a force pushing, squeezing that together in compression. So we have basically unknown forces on either end, but the magnitudes have to be equal because it's a 2-force member. I didn't quite get this perfectly in line, but that'll work out all right. So here is BC in compression and another BC in compression. Now AB down here is in tension. So if it's in tension, tension pulls. It stretches AB out. Okay, so this is AB, same value, opposite direction, AB. And then I have AB pulling here on joint A and pulling here on joint B. All right, so, and I missed, I guess, one force here. I need another pushing here in compression of AC. I think that does it. So there's a whole bunch of different kinds of forces that we're going to look at here in statics. You've been introduced to a number of these. You've been introduced to external forces. We only have one external force here in this problem. It's going to be this force up here, F. You've also been introduced to reaction forces, right? So the reaction forces in this problem are AY, BY, and AX. So once again, this is an external, or you can also call these applied. And then we have our reaction forces. And then we're going to introduce like BC and AC and AB are a new kind of force that we're going to introduce. And what you'll notice here is that these forces are equal, they're opposite, and they're between bodies. Okay, so we call these interaction forces. Because they are interacting between bodies in our overall system. There's going to be one other kind of force that we'll talk about, and we talk about that being internal forces. And we'll explore some of these later in statics, and that's if we cut apart one of these members and expose what's going on inside. We can come up with these internal forces, okay? But for right now, we'll stick with interaction, external or applied, and reaction forces. And so these reaction forces are related by Newton's third law, where we basically have every action has an equal and opposite reaction. And so we find out that that tells us that these internal forces are going to be equal, they're going to be opposite. And essentially, if we put this whole thing back together, they're going to cancel each other out, right? So that's how we can have equilibrium of joints, equilibrium of members, equilibrium of the entire body together, because we've had a canceling of these interaction forces as we sandwich this thing back together. All right, so in order to solve for trusses, there's a couple of different options. One of those options is quite honestly laid out right here, is to take a look at each and every joint. Okay, so each of these joints is a free body diagram. Now, these are concurrent force joints, right? So being concurrent forces, we only get 2 equations for concurrent force systems, just like we did in chapter 3. So we have that the method of joints, fundamentally we sum forces in the x equal to 0 and we sum forces in the y equal to 0. We don't have any available moment equations because our forces are concurrent. So if you summed moments about that point, you basically get sum of all moments equal to 0, right? Because the force lines of action go right through that point. So let's talk a little bit more about this method of joints. So again, the method of joints assumes that if an entire truss is in equilibrium, each joint member and section will be as well. Okay, so we're going to focus here first on joints. Actually, in a later portion of this chapter, we'll talk about sections. Now, the member part of it isn't all that instructive because if we have two force members, we know that every two force member has equal and opposite forces on either end. It doesn't really tell you too much. It doesn't tell you how members interact. It only tells you what's going on with one single member. All right, so if we look at a truss system, let's go with one made of 3 triangles. Let's go ahead and label the points in this truss. We'll call this point A, B, C, D, and E. There's no magic into how you name the points of a truss. It just gives you some reference points. And this is going to be a bit of a cantilever truss. Let's say we're going to put a pin here right in the middle. Right, a pin is a free rotating pivot. So this will be EY, EX, and a vertical force over here, AY at point A. So 3 external reactions, 1 applied force. Let's go with a vertical force here of 10 kilonewtons. Now a lot of trusses hold gravitational loads, so a lot of times the forces are coming downwards, but they can technically hold loads in any direction that you'd want them to. So if we take a look at this truss, one key thing to look for is that if you want to work through joint by joint in the method of joints and solve for unknowns, we know we only have 2 equations at each joint. Therefore, we can only have 2 unknowns at each joint, and we need to have some information, some numbers to solve with. And so not only do we need 2 unknowns or fewer, we also need 1 known. Okay, so a little note here, to solve each joint before moving to the next, we need less than or equal to 2 unknowns, and we need more than or equal to 1 known. Okay, so your knowns either come from external forces or they also can come from previously solved member forces in that diagram. So if we take a look at this diagram, now as you think about what are the unknowns are going to be every single member or every single unknown reaction that comes into a joint. And so if we list out the unknowns, let's start over here at A. A has 1, 2, 3 unknowns. Okay, so there's actually 3 unknowns over here, 2 members and 1 reaction force. B has 3 members. C has 3 members, meeting there at C. D only has 2 members, plus it has the 1 known. So it turns out that D will meet our criteria over here, less than or 2 or fewer unknowns and 1 or more knowns. And then as we get here into E, oh goodness, 1, 2, 3, 4 members and 2 reactions, there's 6. Now realize if you don't have a joint to start with that meets this criteria, then your option fundamentally is to go ahead and treat the entire truss as a free body diagram, solve for these three reactions, and move on from there, right? So if you solve for those reactions, then this joint over here, we get down to 2 unknowns. This one here, we get down to 4. Okay, so you could either start at A or D once you solved for all of those reactions. So in order to do method of joints, like I said, we're just going to draw the joint here. So here is joint D. We have a given vertical force of 10 kilonewtons. Now we're going to assume this is all equilateral triangles, and so these are all going to be 60-degree angles. And I'm going to assume that everything is in tension. And so I have here tension in DC and also a force here in DE. Now I can look at this free body diagram, which does need an axis system, X and Y, and I can tell you that at least one of these forces, and it turns out to be exactly one of them, is drawn in the wrong direction. And I know that because I need a balance of forces. I need a balance of forces in the X. I also need a balance of forces in the Y. I don't currently have that. I have everything pulling up and to the left. So I'm going to anticipate that DC is likely going to be in compression, which means that DC is actually pushing on this joint instead of pulling away from this joint. I'm likely to get a negative value for DC as I work through my equations. All right, so here's my two equations. Sum of the force in the X equals 0. Sum of the force in the Y equals 0. Filling this out with things that I know and don't know. Summing forces in the X, I have minus DE. And then I have a component of TDC, keeping in mind that this angle was 60. So this gives me the cosine. So that will be minus DC cosine of 60 degrees, and this equals 0. And then my forces in the y direction, I only have two of these forces in the y, both of them positive, and so I have DC, and this is going to be the sine of 60 degrees, and then plus 10 kilonewtons. This also equals 0. And so I have one unknown in the bottom equation. I can find that DC is equal to negative 11.5 kilonewtons. Plugging that into the top equation, I find out that DE is equal to a positive 11.5 kilonewtons. Now recognize when I drew this free body diagram, I assumed that TDC was in tension. I assumed that TDE was in tension because of the direction I drew those vectors. I drew both of them pulling on joint D. We know that tension pulls, compression always pushes. Okay, so when I get these answers here, fundamentally this is my direction. If you want to assign, if you think about tension and compression like a direction, these are both assumed in tension. So therefore I've learned that TDC, or the tension in DC, or I just label it DC here, is not in fact in tension. It is equal to 11.5 kilonewtons in compression. Okay, so this would be my answer for TDC, and then this would be a good answer here for TDE. Now, if you wrote negative 11.5 kilonewtons in compression, this is like a double negative. I'm going to look at this answer and say, oh, they meant tension, which you obviously didn't. Okay, so just watch out for that. Treat your tension and compression just like a positive or negative sign. You don't want to add in basically a double negative. All right, so then we go to the next joint, and in this case, I'm going to go up to joint C. So I have one known coming in, I have two unknown members. So we could draw the free body diagram here for joint C. I'm going to assume everything's in tension. So here is my force in BC. I have another force coming down here along this member, assumed tension. So I'm going to assume that everything is in tension, all my unknowns. So this would be my f of BC coming down this direction, my f of CE. Now the question is I just learned that DC was in compression. Okay, so if I'd actually had drawn it correctly on this free body diagram, I should have drawn it pushing down on this joint. So my question for you before we move on is, should I draw, now that I know the direction of the force in DC, should I draw it going up to the left or down to the right here on joint C, right? This was C and this was D. Up to the left or down to the right. We know that TDC is in compression. Sorry, I keep saying T in front of it. In some of my notes, I often label it like a tension in DC. Here I just labeled it as the force within DC. Let's actually go with that convention here on these two as well. So let's just call this BC and this one CE. All right, so back to DC. It is in compression. Compression pushes. Therefore, we need to have that pushing here on C. So this would be my DC. So one thing to mention about as we move through these problems, just put it right here, is always bring correct information to the next joint. Okay, so once again, if you're solving these algebraically one by one, you always want to bring the correct tension or compression information. You're also going to bring the value here, as going to be equal to 11.5 kilonewtons, just like you would include the correct direction and value of an applied force, right? It acts in the same way as we get into this next free body diagram. We then, with some forces in the X, with some forces in the Y, we could solve for those next two members and work our way around. And so we started on this problem. This was step 1. We then moved into step 2. From C, we could go over to B. That would be step 3. We still have too many unknowns there. And you can mark these off as you go if you want. So we solve for this one and this one at D. We solve for this one and this one at C. So at B, we have two unknowns. We could solve for here and here. Then you'd have your choice. Now, if you'd already solved for EX and EY, then you could jump down to E. If you hadn't, you could go over and solve for AY and this member, and then basically if you wanted to check everything out, you could close it by solving for EX and EY. And in many things in statics, you can solve them multiple ways, right? You could solve for EX and EY externally and then check them internally, a bunch of different ways to go. But that's the idea of a method of joints problem, is that we find a good place to start. If we don't have a place to start, we take a look at our overall truss free body diagram. We solve for some of these external reactions, just like we would out of chapter 5 with a rigid body. We then jump into doing two equation, two unknown from a concurrent force free body diagram of each joint. I assume often that everything's in tension, and then I use my math to check out if it's in compression. You can guess if you want up front, and then essentially in your equations, you always just need to make sure that whatever axis system you use, you assign positive and negative according to that axis system, right? So once we write our equations of equilibrium, it doesn't matter where we get our free body diagram from, we just use it to assign positive and negative according to that axis system and solve out things algebraically. So that's the big picture of method of joints and also trusses. Welcome to the new chapter. I hope you're having a great day.